I welcome us back again to our revision class on Physics 191, which is also called the Physics Practical. Okay, so just like I did in the Chemistry Practical, I'm going to do same in Physics Practical. I'm going to teach us some vital things we need to know. Then later we'll now deliberate with the past question. Okay, first of all, we'll look at plotting graph. That is the first. Want to know some points that you need to note when plotting graph. These points are the points that are being marked. If these points are present, you score mark. If they are absent, you lose mark. So whenever you are finished plotting your graph, ensure that these things I'm going to call out are present. Then you are sure that you have scored as maximum point as you wish to have. Number one, each graph should have a title or heading. Number one, we'll talk of heading or title. Heading or title. Like some might ask, what do you mean by heading or title? If I want to plot a graph, for example, now I want to plot a graph. I will now say this: I should plot a graph of M against X. So at the top of the graph sheet, I will write graph of M measured in gram against X measured in centimeter. This is the title. Every graph must have a title, or you can call it heading. Without the heading or the title, we don't know the graph you are talking about, and we don't know the essence of that graph. So every graph must have a head, a title, or a head. That is one. Number two, we said that both axes must be properly measured, labeled. Both axes must be properly labeled. What do we mean by this? If we have, this is your Y, this is your X. These are the labeling of the axis. If I'm plotting a graph of M against X, then here will be M, here will be X. You must properly label your axis. You must properly label your axis. That is two. Number three, choose a suitable scale. Now, you need to choose a very good scale. The scale is so important that it tells how big or small your graph might be. So you must choose a suitable scale. So remember that when choosing scale, when you have graph, this like your graph like this, we have, if you count 1, 2, 3, 4, 5, if you measure it with a meter rule, you have it to be 1 centimeter. Do you understand that now? So 1, 2, 3, 4, 5. If I have 10 of it, 10 of it will be 2 centimeter. 5 of it is 1 centimeter. So I can say let 2 centimeter represent 5 units. It means for every 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, I will write 5. Another 10, I will write 10. Another 10, I will write 15, 20, like that. So if I say let 2 centimeter represent 5 units, that means for every 2 centimeter means 10 of this box. 5 of it is 1 centimeter. So 10 of it will be 2 centimeter. So let 2 centimeter represent 5 units on y-axis. Okay, you can also say let 2 centimeter represent 10 units on x-axis. I've just chosen a scale. It might not be exactly what I'm writing. You can be let 1 centimeter here. 1 centimeter can represent 5. Would I here 2 centimeter can represent 10 units, depending on how you want your graph to be. But one thing you must know is that whatever scale you choose should ensure that the graph covers the checkbook of the graph sheet. Ensure that the plotting of the graph covers the checkbook. That what I mean by checkbook is something like this. You know your graph sheet, it goes something like this. So if you plot your graph, let it cover something like this. Okay, so that this graph now covered not something like this. Don't plot something that is too small. Don't plot something that is too small like this. And you now plot your graph like this. This is very wrong. This is too small. This is okay. So be very careful. And it is the scale you choose that will determine the size of this or this. So let's be very careful about that. So after choosing the scale, then I think these 3 points are the most important points you will need in plotting your graph. These 3 points, they are the most important points. Then the next one is choosing the proper line. Choosing the proper line. Let me put up that. When you want to choose a proper line, example, I have something like this. This is my graph. I want us to look up very well. And I've plotted my graph. This is my graph. And I've taken, okay. No, let me put on this. Now, I have something like this, like this, like this, like this, like this, like this. Now, my best line is that line that when you use your ruler, you take your best line. This is my best line. Now, if you watch this, my best line, how do I know that I'm correct? My best line is correct. Now, how many points did I plot? I plotted this 2, 3, 4, 5, 6. There are 6 points plotted. In these 6 points now, it's not must that all of them must enter. In fact, all of them should not enter. Just know that one. All of them should not enter. It's must that all of them must not enter. There is a reason for that. Now, I plotted 1, 2, 3, 4, 5, 6. If 3 enter, it's okay. If 2 enter, it's okay. In fact, half of the total number of points plotted is expected to enter. So I have 6, half is 3. So if 3 enter, it's okay. Now, if I finish plotting here, sometimes I want to tell us, do you know that if I wish 3 to enter, this one is very close to the point. I can decide to clean it and put it on the point. It doesn't make any difference. Are you getting that? Now, another thing is that the points that did not enter must be distributive. In that, if all these points that did not enter, now these 3 that did not enter are in one side, you are wrong. They have to be distributed. Like 3 did not enter. 2 can be in the right hand side, 1 will be in the left hand side. Even if like 5 did not enter, 4 can be one side, then somebody must be here, something must be there. That's what we are trying to say. So if you watch now, 2 is here, 1 is here. The ones that didn't enter. Now, what am I going to do with them? I'm going to use them to get what we call our vertical scatter. Okay. You look for the one that is farthest. The one where far pass. Farthest away from the best line. This is what I call the best line. This is my best line. You look for the one that is farthest away from the best line. If you check this guy and this guy, she said this guy they far from here past this. This one is more closer. Then here I don't need to check because this guy is the only one here. So is the only one to represent. So you put your ruler perpendicular also along the same best line. You put your ruler the same way. Then you take a cut on this one now. It must be a broken line. It must be a broken line. Then you also take for here. It must be a broken line. Okay. Now at this point now, these ones I've cut them to create my vertical. I will now join one of this line to this line. Watch what I'm going to do now. I can join like this. This line is perpendicular to this. So if I join them, they are equal. Now, on this line I have joined. You can join it anywhere. You can come here and join. You can go anywhere you like join. Then you write W on top of this line you have. Please, very, very important. All these things I'm saying are very important. You write a W on top of it. This W now mean vertical scatter. Okay. Then, remember that this is how we get our vertical scatter. Now, to draw us back again, the best line must be that line that can take at least half of the points plotted, whereas the ones that are not plotted are distributed at the right and the left hand side. That is one. Then the ones that are distributed at the left and the right hand side, the points that are farthest away from the best line are taken for vertical scatter. And then we draw a line perpendicular to the best line also, but they are going to be broken lines. They are going to be broken lines. Then we join any point here to any point here because we know it's the same. And on top of it, you write what? A W. So this is how we get our vertical scatter. Now, the next one is how do you get your slope? Let me draw it out again because I know that one will have been rough. Now, if I have my graph to be like this, now I want to get my slope. There is no hard and fast rule of getting slope line. I can start from a point and end at a no point. Example now, but let it be sizable. Please, slopes are not small, like you just have something like this. Slopes are not small. Slopes are big, as in 1/4 of the whole graph. My slope can be like this. This is what I've done. But one thing is that don't pick the last points. It's not always advisable to pick the last points. You can even pick like this. You see? So you can see the way I've taken my slope. This slope is this line of slope is very, very is almost more than 1/2 of the total graph. It's not as small as this. Now remember that these ones that they enter are our vertical scatter. So this is how a complete graph should be. I will name my axis. I will take my scale. I will take my title. And I'll take a best line joining this and write W on top. Okay, I believe these things are well understood now. So these are some few things I need us to know about plotting graph. We move to some other thing. So I believe you know that and you have been plotting graph from your manual. So by now you should have known how to plot graph. So we'll go to straight line graph. Equations of straight line graph. Equations of straight line graph. You know that when you come to physics practical, most of the graph we draw in physics are always straight line graphs. So An equation of straight line graph is given as y equals to mx plus c. This equation of a straight line. Any straight line has this equation. Now, y is the y-axis. This x is the x-axis. Now listen. Any person attached to the x-axis by virtue of multiplication, any person attached to the x-axis by virtue of multiplication is your slope. Slope is equals to m. And any person attached to the x-axis by virtue of plus or minus is your intercept. Intercept is c. I repeat, y is our y-axis, x is our x-axis. Anybody attached to the x-axis by virtue of multiplication is our slope. And anybody attached to the x-axis by virtue of plus or minus is our c. Please take note of that. So that is the equation of a straight line. Now, in experiments we do in the lab, in physics practical, they have their own theoretical formulas. So if you want to, maybe I finish plotting a graph. If I know the theoretical formula or theoretical equation that guides the experiment, I can determine how the graph of that experiment will go. Whether it's going to have intercept, or whether it's going to come from the origin. And how do I do that? I do that by linearizing that equation. So we're going to see some experiment we did in the lab or in our manual and see how we can linearize them to look like equation of a straight line, and it will now tell us how the graph will actually go. So it's not by magic you know how a graph will go. Okay, let's take, so we're going to what we call linearization. Linearization of equations of straight line. Now, linear means straight. Linear, to linearize, to make something a straight line. So we'll take one example. Example 1, equation of simple pendulum. Equation of simple pendulum. Now, when you talk about equation of a simple pendulum, you know, when you come to simple pendulum, we have one equation like this, 2 pi root of L over G. This is an equation of simple pendulum. So now, you perform this experiment in the lab, and we have this equation now. We want to linearize it. What do we mean? What do we want to actually do? We want to make this equation to look like equation of a straight line. And by the time we have made this equation to look like equation of a straight line, we will now know how the graph is supposed to look like. Okay, now, if I'm to plot graph of L against t squared, so they've given me a leverage. I can plot a graph of L against t squared. I can also plot a graph of t squared against L, whichever one. It depends on the one the examiner told me, but this is the one I've seen in our manual. You're plotting a graph of L against t squared. So I'm going to linearize for L against t squared, and I'm also going to linearize for t squared against L. Okay, so let's see something here. So for me to linearize, get a linear equation from this for L against t squared. What I mean by L against t squared is that L becomes the y-axis, t squared becomes the x-axis. So we will now come here. If for me to get this L, I need to remove this root. So I will say I square both sides. While we are squaring both sides is for us to remove this root. And if we square both sides, we'll start seeing our t squared, which we want to use as our x. So having squared both sides, we are going to be having t squared is equals to 4 pi squared L over G. Is that clear? Okay, now, since our L is going to be the y-axis, so the L is supposed to come here, compare it with this. Look at y should be here. Whatever is going to be the y-axis should be here. So L is supposed to be our y-axis, so it should come out. Whatever is going to be our x-axis should be after the equality sign. So after this equality sign, whatever is going to be the x-axis should go there. T squared is our x-axis, supposed to go there. So I cross multiply. I have 4 pi squared L equals to T squared G. So that my L becomes T squared G over 4 pi squared. Okay, at this point now, my L, which is going to be my y-axis, is here. My T squared, which is supposed to be my x-axis, is after the equality sign. So I think I'm true. Once you can do that, then you are true. Then, if you compare this with the equation of a straight line, that means L is my y-axis, T squared is my x-axis. So I will now say L is equals to y-axis. Are you there? T squared is equals to x-axis. Now, anybody attached to the x-axis by virtue of multiplication is our slope. Now, if you check the whole of these people, G over 4 pi squared is attached to our x by virtue of multiplication. So they are going to form our slope. Now, if you watch, there is nobody attached to the t square axis by virtue of plus or minus. Hence, we don't have intercept. So here, intercept is equals to 0. We don't have intercept. So for the intercept to be 0, it means that if you plot this graph, it's going to come from origin. That means if I plot this graph, I'm going to be having something like this. That means if I plot this graph, I'm going to be having something like this. My L measured in centimeter, my T squared measured in second squared, please. I should have my title graph of L in centimeter against T squared in second square. Are you seeing the way I put my title or my heading? Then I should have my scale. Let me say I'm using 2 centimeter to represent 5 units on L centimeter axis. And I'm also using, let me say, 1 centimeter to represent 2 units on T square second square axis. This is my scale. You know, I just forged the scale. So you know the one. If you check your own, you know the one that I mean. So I have my heading. I have my X and Y axis well labeled with their unit of measurement. I have my scale. So this graph now, because you know get intercept, its intercept is 0. Remember that this place is 0. So it will come from the origin. This is how this graph will look like. How do I know it will come from origin? Because the intercept is at 0 and 0 is at origin. So I can take my slope. And if I take my slope is the y over the x, which is equals to g over 4 pi squared. That's my slope. So this is a skeletal view of what we have got. So for that simple pendulum experiment, the graph is going to be a straight line graph coming from the origin. Why? Because if you linearize that to form equation of a straight line, that is what you're going to see there. So I believe that is very. We'll take another one. That is, we call this one 1. Take another experiment. Okay. Okay, the next one we're supposed to look at is effective mass of a spiral spring. This is another experiment we did in the lab. So we want to linearize this equation of a spiral spring and see that when we do experiment of a spiral, effective mass of a spiral spring, how will the graph go? We can only know that by linearizing the graph. Now, before I do this, I think something came to my mind. Also in your manual, you are given something like this. There is this experiment for simple pendulum that went like this. Now, here they say we should plot a graph of h in centimeter against t squared. So I want to just quickly show us what will really happen here. So we have t squared is equals to 2 pi all squared root of h minus h over g. At this point, we have t squared is equals to 4 pi squared root of h, okay, all squared here, so that this root will not follow us again. We have h minus h over g. Is that clear? So since our h is going to be the y-axis and the t square is going to be the x-axis, see the h here, that's supposed to be the y-axis, supposed to come before the equality sign, while the t square will go after the equality sign. So what I'm going to do is to cross multiply. I have 4 pi squared into big H minus small h equals to t squared g. Okay, now I divide both sides by 4 pi squared, so I have h minus h equals to t squared g over 4 pi squared. Now, at this point, I only need the small h to remain here. So I'll push the small h here because it's carrying minus. I push it here to become positive while I bring this one here. So I'm going to be having big H minus t square g over 4 pi square is equals to small h. This one went like this, became positive. This one came like this, became negative. Or small h becomes big H minus t squared g over 4 pi squared. This and this are the same. The sign will only change if you are not moving all of them. Like if I want to move only this h now, the sign will change. But if I'm moving the whole of this, sign will not change. If I'm moving the whole of everything this side, sign will not change. So that's why my sign has not changed here. So this and this are equal. So looking at this point now, from what we have got there now, my h is my y-axis. My t square is my x-axis. Now, this is my y-axis. This is my x-axis. Anybody attached to the x-axis by virtue of multiplication is my slope. So my slope there is g over 4 pi square. I believe you know that. So that's my slope. Now, anybody attached to the x-axis by virtue of plus or minus is my intercept. So intercept is equals to what? H. Now, but if you watch something now, this my slope. If I remove this my x, you see that this minus belongs to g over 4 pi square. So it's a minus g, meaning that I'm going to be having a negative slope here. I'm going to be having a negative slope here because if you remove your x, this minus is supposed not to affect your x or your y. There is no plotting minus x against minus y. Both of them should be neutral. So if I remove my x, see that this is minus g over 4. So it's a negative slope. Unlike the one we did before, it's a positive slope. So let me still put my t square there. So I have a negative slope. What does it really mean to have a positive slope and to have a negative slope? I want to show us something there now. If I have a positive slope graph, it will look like this. This is a positive slope graph. But if I have a negative slope graph, it will look like this. Just, you see this graph is positive slope. You see this graph is negative slope. So from what we did, this second one I did for you, that we have h against t square. This is how the graph will go. Why? Because a negative slope is to go like this. But if it's a positive slope, this is a L against t square. It's going to go like this because it's a positive slope. Okay. Now, Let me show us something. I want to show us something that is very vital here now. Why is it actually negative? Does it show negative? Yes. Let me show us something that is very vital now. Okay, let's assume things like this now. I want to get my slope is y2 minus y1 over x2 minus x1. Now, this is positive slope. That means the answer I'm going to get from this slope is supposed to be positive. So, where's my, if you know that if you check from this slope, this is standing, so this is y, this is lying down, so this is x. So my y has top and bottom. My x has top and bottom. So if I'm looking for the y, y2 is the smallest y. There is top y, there is bottom y. Top y is 4. Do you see that? That is a bottom y is 2. That is my y1. 2. Top y is 4. 4 minus 2 over bottom for x. Now, what's something? I want you to get something. The one we choose as x2, the one we choose as x2 is the one, see this thing, you see that this x and y meet here. Are you seeing something? This x and y, they meet here at this point. They meet here. So this becomes my x2. Y, the one that is joining the line becomes my x1. This one is my y1, my y2. Why this place that they join is my y1. Now, my x2, if you trace it down, is 15. Why my x1, if you trace it down, it's not like minus 5.5, let's just say. Then if you do this, you will now have this is 2 over 15 minus 5.5. That is 9.5. So that my slope becomes 2 divided by 9.5. Will give me 0.21. 0.211. So this becomes my slope. If this is my graph, this becomes my slope. And if you watch, this slope is positive. This slope is positive. Now, when we talk about a negative slope, what do we mean? Watch out now. Now, this is a negative slope. So my slope is going to be y2 minus y1 over x2 minus x1. Still just the same thing. Now, for how I'm going to do it now, remember that this is my y. Hope you know why this is my x. Now, my y1, my y2 is always that point that is, hope you know this is my y2. This one is my y2. Why this place is my y1. Hope you know. So my y2 is going to be 6 minus 2. Then the problem comes in the x. Remember I said our x2 is always that place that the y and the x join, this point. That's where always it be our x2. So if you watch now, my x2 should be around 5.5. Then my y1, the one that touches the line, which is going to be around 15 here now. So if you do that mathematics, you see that 6 minus 2 is 4. Whereas 5.5 minus 15 will give us minus 9.5. Minus 9.5. And if we do 4 divided by 9.5, 0.421. This will give me minus 0.421. You see that my slope is a negative slope here. You see it. So I'm going to be reporting a negative slope where the thing actually came from the x side. Because that point where the x and the y join is always my x2. And the value of that point is smaller than the one I take that joined with the line, which is always my x1. I believe this is very, very clear. Please don't make mistake about this. So I've just told us that there is something we call negative slope and there's something we call positive slope. In your graph, the simple experiment graph that you did in your manual, the graph of L against T square was a positive slope, while that of H against T square was a negative slope. So this is how that one's supposed to look like. So we are through with this now. So we return back to linearizing this. If I'm to linearize this, in this one, they say we should plot graph of t square against m. We should plot graph of t square against m. So that means I need t square and I need this m. So I'll square both sides. So I have t squared is equals to 2 pi squared root of m plus mo over k. K is a spring constant. Hope you understand. All squared. So we have t squared equals to 4 pi squared m plus mo over k. Now, since I'm plotting a graph of t squared is already here, so I don't need to move it, against m. So m is here. So this becomes t squared equals to 4 pi squared m plus 4 pi squared mo over k. I take us to this side. You know, this thing becomes t squared equals to 4 pi squared m over k plus 4 pi squared mo over k. I believe you remember that you know that this and this are the same. Now, since my t square is my y-axis, my m is my x-axis. So this one is my y, this one is my x. Anybody attached to the x by virtue of multiplication is my slope. My slope is 4 pi squared over k. And anybody attached to the x by virtue of plus or minus, all of them becomes my intercept. Intercept is 4 pi square mo over k. So it means that if I plot this graph, it's going to look something like this. A graph of t squared against m. A graph of t squared against m is going to have an intercept. It's a positive slope. Hope you know, a positive slope. So it's going to have an intercept. I mean, it's not going to come from the origin. So it's going to have an intercept around here. How is this intercept determined? It is when you draw your best line, it will tell you where the intercept is. So then let me clean up this, not looking. Okay, then this is my best line. I take my slope. So this my slope, the y over dx is its value will be close to something like this. Okay, so this is my y, my x, my slope. Then this is my intercept, this place now. The place that the line cross the y-axis is called my y-intercept. place that the line called my y-axis is called my y-intercept. And that is my, my slope, this one I intercept. My slope is 4 pi squared over k. While my intercept, c, is equals to 4 pi squared mo over k. Okay, so you see what we mean by linearizing the equation. If you linearize, that means this is how this graph will go. That means if I have to plot a graph of in the effective mass of a spiral spring experiment, if I have to plot a graph of t squared against m, it's going to give me an intercept. I'm going to have an intercept. Okay, and it's going to be a straight line graph. It's going to be a positive slope, not a negative one. So all these things are the vital information we get from linearization of an equation of a straight line. We look at another example. We look at another. In this case, we have a focal length of lenses and curved mirror. So this is the equation of a mirror. You remember? Now, if we have to plot this, if they say we should plot a graph of 1 over v against 1 over u, that means 1 over v becomes my x-axis, while 1 over u becomes my 1 over v becomes my y-axis, 1 over u becomes my x-axis. That means, coming to this equation now, 1 over v will remain here, while 1 over u will go to the other side. If you compare with the equation of a straight line. So I'm going to be having 1 over v becomes 1 over f, or you can say it is a minus 1 over u plus 1 over f. So that y will remain here, x goes here. So that means my y-axis is equals to 1 over v. My x-axis is equals to 1 over u. It's not equals to minus 1 over u. It's equals to 1 over u, not minus 1 over u. So my slope becomes anything attached to my x by virtue of multiplication is my slope. The only thing that is attached to this x is this minus. So, which is like minus 1. My slope becomes minus 1. Then my intercept, c. Anything attached to this x by virtue of plus or minus is my intercept. My intercept becomes 1 over f. I believe this is very clear. This is my x. Anything attached to this x by virtue of multiplication is my slope. So only this minus 9 attached to this, and this minus is also called minus 1. So 9 be this. Then anything attached to this guy by virtue of plus or minus will give me my intercept. Now, if I'm to plot this graph like this, it's going to look something like this. It's going to look something like this. I'm plotting a graph of 1 over v against 1 over u. So it's a straight line graph, a positive one indeed. Now, if you watch something now, my slope is minus 1. So I'm going to be having a negative slope. My slope is minus 1. So I'm going to have a negative slope. So it's not going to be a positive slope now. It's going to be a negative slope. A graph of 1 over v against 1 over u. So my dy over dx is equals to minus 1. That's my slope. So this is my y, this is my x-axis, and I've got my slope to be then. My intercept, where this thing cuts the y-axis, my intercept c is equals to 1 over focal length. So you see it. So my intercept is 1 over f. Look at where it is here. Whatever value is here is my c. Then the y dx is minus 1 because it's the slope. Okay, so this is how the graph will look like. So if you have to plot a graph of 1 over v against 1 over u, you will see that this is how the graph will look like. So this is how we know how our graph will look like. We don't cram it. You have to linearize. If they give you the equation, you have to linearize. So sometimes someone will say, but they don't give us this equation in the example. Yes, the way I'm teaching you, your mind should be there. When they say plot a graph of, you should not, oh, I've learned it, it's going to be like this. Okay? So you have to have it up there. All these things I'm teaching you, if you want to plot graph, they will not move away from any of these, what is in your manual and what I'm teaching you now. Okay, so that is for focal length. Okay, we look at the next one. There are some equations that look exponential. There are some equations that look exponential. So let's look at that and see how to take care of that. This one is exponential equation. Example of the period of a vibration of a cantilever. This is how the equation looks like. Now, if you watch, it's carrying an x. And this case is constant. Now say I should plot a graph of t against L. So what I'm going to do is t is already my x-axis. Okay, YL is my t is already my y-axis. Let me say plot a graph of L against t. Whichever one is okay, but I want to make it more tedious. So I'm going to be having up there. We're going to be having t is equals to k l x. Now I need to deal with this guy. What I'm going to do is to take log of both sides. That is why I'm teaching you about exponential equation. We're going to take log of both sides. So I'm going to have log t is equals to log k plus x log L. This is what I've done. So since I'm plotting a graph of L against t, this L should come here. Why this t should go here? So I'm going to be having x log L minus equals to log k plus log t. Are you following that? Now, remember that since this log L is our y, this x should leave. So I'm going to divide both sides by x. So I'm having log L to become log k over x minus plus log t over x minus. Are you following that? I'm dividing both sides by minus x. That is, if I do this minus x, it cancels this over minus x. The minus goes up to look like this. This over minus x. The minus goes up to look like this. So, since we are plotting a graph of L against t, so L is already here and this is our t. So, my y-axis becomes log L. My x-axis becomes log t. Log t, only log t will be our x-axis. Then my slope becomes anybody attached to the slope by virtue of multiplication is anybody attached to the x-axis by virtue of multiplication is our slope. So I'm going to be having minus 1 over x. Do you know that? This times this will produce this. So that's my slope. Then my intercept, which is my c. Whoever is attached to this guy by virtue of plus or minus is this. So it's going to give minus log k over x. So this is it. Okay? So this is it. So if I plot this graph, it's going to be looking funny like this. I'm plotting the graph of log L against log t. It's a negative slope. You see that? So I take my slope, having an intercept c here to be minus log k over x. Why my slope? My slope is the y over the x, which is equal to minus 1 over x. So this is my y and this is my x. So that's how it's going to be. But then if they say I should plot a graph of t against L, it's going to look different. See what it's going to be. So my t is already there. So I'm going to have t equals to, I'll take log of both sides just to remove this, to drop this x, equals to log k plus x log L. So if I'm plotting a graph of t against L, t is already here, so I don't need to move it. So what I'm going to be having here is that now my y-axis is equals to log t, my x-axis is equals to log L. Then my slope, anything attached to the x-axis by virtue of multiplication is my slope. You see how this one slope is minus 1 over x, or this one now the slope is x. Then my intercept is log k. You see the difference? See, that's why I said let me pick this one first. This one looks kind of tedious and show us what really happened. Now, if you watch this one, now it's a positive slope. If you plot this graph, we have log t here, we have log L here. It's going to be a straight line graph, a positive slope. We have our dy over dx here to be equals to x. Okay, but it's not, it has intercept, so it's not going to come from the origin. So it's not going to come from the origin. So it's going to have an intercept where you take your best line and ensure that it has an intercept. So this intercept now, c is equals to log k, while my slope is equals to x. So this is 2. So mark this about exponential equation, the equation that has a power. So once you want to take the, instead of taking the other one, you say you take square of both sides, but this time you take log of both sides for linearization. Okay, I believe that is very, very good. The next thing we'll go into is curved graphs. Some graphs are curved and we want to learn about them. So we'll go into what we call curved. Okay, now we want to look at, we have just looked at straight line graphs, but in physics practical, there are also curved graphs. There are also some experiment that talks about curved graph. So this is a curved graph in physics. We have 3 types of curved graph we see in physics. One is parabola. When it's parabola, it is either like this or like this. The other one is hyperbola. Why this one is exponential? Watch exponential graph. Look at how it goes. This one goes as if it want to touch the baseline. So these are the 3 types of curved graph we have in physics. Now, if these are the 3 types of curved graph we have in physics, then we want to see some experiment that actually goes with curve, experiment of curves. So we'll look at some examples. Okay, we want to start with Boyle's law. We want to convert the equation of Boyle's law to a straight line graph. But then I want to make a little correction. Remember in the first time I said the equation of a Boyle's law equation is a curved graph. Okay, the mistake there was that if I plot if I plot a graph of P against V, it's going to be like this, not P against 1 over V. But if I plot a graph of P against 1 over V, I will have a straight line. Please mark this. Correction to the what I said in the former time. If you plot a graph of P against V, it's going to be a curved graph. But if you plot a graph of P against 1 over V, it's going to be a straight line graph. So please, for us to convert this now to a straight line graph, you are going to be having that P is equals to K over V, or P is equals to K times 1 over V, just the way we did the other time. That's supposed to be the conversion from curve to straight line, while this is the curve. If you plot a graph of P against V, you have curve. Or if you convert it from here to look like this and plot a graph of P against 1 over V, you are going to have a straight line graph. So we have to look at another example. This one we look into is equation of motion. So if I want to convert this equation of motion into a straight line graph, I just need to do what I'm going to factorize for the t here. We have factorized for the t. T is common. If you factorize, you have this. So that this times this will still give me this. This times this will still give me this. So once I factorize, divide both sides by t, then I have s over t. And if I divide the whole of this by t, t will go, I have the whole of this only. Or this can also be called this. That is half at, same as at over 2. So when I have this equals to this, then if I plot a graph of s over t against t, Plot a graph of s over t against t. I have converted this equation to a straight line graph. See what it's going to look like. So we have my y-axis will be this. My x-axis will be this. Are you there? My y-axis will be this, or let me use this. My y-axis is this. Sorry, my y-axis is this. My x-axis is this. Anything attached to my x-axis by virtue of multiplication is my slope. So it has intercept, so it's not going to come from. So my dy over dx here is a over 2. My dy over dx here is a over 2. Then anything attached to this t by virtue of addition or subtraction is my intercept. So here is my c, which is equals to u, initial velocity. So this tells me the initial velocity of the motion. If I plot s over t against t, I will have this. This is, I've converted this curve equation or quadratic equation to equation of a straight line. So I can get slope, and as I can get whatever information I need from there. I believe if in the exam they ask you to convert a curve equation to a straight line equation, if they give you something like this, you should be able to do it. This thing don't come out for exam before. It's one of the past questions. So master it. So we move to another thing.